Welcome. This is Exploring Elixir Processes Through Music. I'm Stephanie. I'm human. I played violin for a very long time. It was my professional career for a while, and now I am a software engineer at Cars Commerce. Speaking of Cars Commerce, if you want to stay in touch, submit your info or check out our careers page. We have our 2 QR codes here. Or there's a lot of us over here from Cars Commerce. Please come talk to any one of us. We're happy to talk to you. All right, let's talk about our roadmap. Getting started, we're going to go over a glossary of terms just so we're all on the same page. We're going to talk about the process lifecycle, the library that we're using to play notes, which is MIDI synth, and then we're going to get into the fun stuff: spawn, tasks, gen servers, and supervisors. So glossary. We're going to talk about a lot of terms here. Just want to be all on the same page. Anonymous functions. We've kind of talked about this a little bit in some other presentations this morning. So this is just passing around executable code just like a string or an integer. You evaluate it with what you say it is, period, and then empty parens. In this case, we're always using zero arity functions. There's guards, is function 1 and is function 2. Is function 1 just takes the name of the function, is function 2 takes the number of args. You can also use a capture operator, but we're not using that in this presentation, so don't worry. This is an example of just an add function, anonymous function, which is just doing 1 + 1, and then how to call it. You'll see this a lot. MFA, we talked about this in a couple other presentations this morning as well. It's module function argument. So module as your module name, function as an atom, arguments as a list, and we use this a lot in this case for kernel apply 3. So let's look at our example. We have my module, multiply, and it takes in 2 arguments, and this is how we'll call it. You'll see this a lot: apply, my module, multiply as an atom, and then the list of the args in order. All right, PIDs, or process identifiers. Each Elixir process has one. It has a type and a guard, and you can see an easy way to see a PID is just get into your IEX shell and run self, and that's your PID for your shell. All right, fun stuff. Let's talk about process life cycles. So there's always 3 parts of the life cycle: creation, execution, and termination. So you'll always create the life cycle, execute the code, or create the process, execute the code, and then terminate the process. Termination can happen because of a code issue. In execution, it can happen by an outside source, or just the code finished executing and then it's terminated. All right, so MIDI synth is the library that we're using to play our notes. You can find it at this repo. How you start it is with a start link. Don't worry about that for right now. We're going to talk about that later. So MIDI synth start link takes an empty list as args and returns an OK tuple with a PID back that we're just calling synth. So these are the notes that we're going to use for the majority of the presentation. It's going to sound very familiar to you. In the public domain, it is Twinkle Twinkle Little Star, the first 2 phrases. So the note args is synth, which is that PID, and then the velocity of the note, which is just like how it sounds, the time in milliseconds that it's played, and then the dynamics, or like how loud it is, the volume. All right, more fun stuff. Spawn. Let's talk about how to like make some processes. Spawn 1. This takes an anonymous function, just like we talked about, and returns a PID, just like we talked about. So let's name our anonymous function. We're just going to do play a note with MIDI synth, and then we're going to spawn that function, which returns a PID. And at the end, we can call process.alive on that PID, and we'll see that it's false because it's already terminated. So we create the process, we execute the code that's in the anonymous function, and then it terminates after it's complete. So the whole process life cycle. And that's what it sounds like. Pretty cool. Now, spawn 3. This takes in an MFA. Same thing, just returns a PID. Same thing here, process.alive, false at the end. Let's do something a little bit more fun, let's say. We're going to iterate through all of the notes, And we're going to spawn a process for each one to play it, and then we're going to process sleep for 1 second in between, just because computers are fast. So yeah, that was great, right? You heard the first 2 phrases of Twinkle Twinkle. You have each process spawned, each process completes a life cycle, right? It creates, it executes that code, and then it terminates. So we had, I believe, 14 notes that we played, so we had 14 spawned processes in there that went through the full life cycle. We're going to talk about monitors just very, very quickly. You can spawn a monitor to kind of monitor a function. You don't really do this in practice because agents and gen servers and supervisors, all that does that for you in tasks. But you can spawn a monitor. It's only one way. It notifies you on exit, and then you can flush it to actually get the down message. So in this case, spawn monitor takes in an anonymous function. We're going to raise here just for our example, and you return a tuple of a PID and a ref. And it sounds the same. Just playing that one note. So this is what it looks like. We're calling our spawn monitor, which is just sounds.monitor.monitor in this case. It's the exact same code. So we get back that PID of 0.187.0 and a ref. And then we get that runtime error of raising here. And then if you flush it, you get the down message with the process, same PID here of 0.187.0 with your runtime error and where it failed in the code. Okay, let's move on to some more fun things with task. Task async. We've seen this a couple times in presentations this morning too, so that's pretty nice. We have 2 options of task async 1 and task async 3. Just like spawn 1 and spawn 3, it takes either an anonymous function or an MFA. It always returns a task struct, which has an MFA, caller PID, and then the task PID, and then a ref, which we don't really do anything with. It always executes one thing before shutting down, and it awaits a reply. You can do this by using task await1 or task yield, and you just give that the task, and then you can manually shut down a task by doing task shutdown. Now, if the caller crashes, that caller PID versus the task PID, it'll crash the task. Okay, so in practice, you can see task async. We're using the MFA here, so same thing, same note, and then we get that task struct back with the MFA, which is a tuple of the module, the function of play, and the number of arguments. The owner PID and the regular PID, or the task PID, is here, and then a ref. So let's iterate through and do a task await after each task async and see what that sounds like. So great, that sounds almost exactly the same as the spawn, so how is that different? Well, we're not doing a process wait or a process sleep, we're just awaiting each task to complete. So every time it completes, does its PID, terminates its PID, and then we get the notes back. So a little bit better, we don't have to add that process sleep, so we're like getting a little bit more advanced here. The next one is, what if we don't await any of the tasks? This is kind of like pre-await many. Let's do the same thing. Sounds, yeah. I don't know what that was, jazz. So my jazz dance. Yeah, that sounds like we just sent all of the notes out all at once, all the PIDs complete, and then we're not awaiting each one, so it just happens all at once. Truly async, right? Cool. Oh, that's gonna play again. All right, now we can await many. So this takes in multiple tasks, it returns the replies of the tasks, and await many can only be called once. If you want to await many, or if you want to call it multiple times, you do yield many. So in this case, we're giving it task await many. It can have a list of tasks and then an optional argument of a timeout, which the default is 5,000 milliseconds. So we're just giving it 5,000 milliseconds. So the exact same thing that just happened, right? So we just kind of did a task await many without the await before. Same thing. Let's throw a wrench in this now. Now we have an anonymous function of oh no, which just does a process sleep of 100 milliseconds and then raises oh no. So what we're going to do now is have a task async playing 2 notes at the beginning, our oh no anonymous function as a task in the middle, and then 2 notes at the end. We're going to do a task await many and see what happens. You can do it again. It's very fast. So this, like, what we talked about, how it crashes the color process, our middle task, our oh no, that raises after 100 milliseconds, so it sends out all those async tasks at the same time, it plays all 4 notes for 100 milliseconds, and then when it raises, it automatically crashes up. So we get the runtime error and then the exit. Oh, it's going to do it again. Cool. So now we can move on to streams. So task async stream 3 and task async stream 5. Just like the other functions, it takes an enumerable of anonymous functions or enumerables of MFAs, and then it has a bunch of options that we'll talk about in a minute. It returns a stream, and then each element of each enumerable is processed in its own task concurrently, which we'll talk about in just a moment. Let's do some options. So this is where it gets a little bit fun. Your max concurrency you can set as your scheduler count. So you can know the default of your scheduler count, like if you're on your own IEX session for your own computer, you can do system.schedulers online. That'll give you the number of cores that you have, and that's your max concurrency. So you can change that. Ordered is defaulted to true. This has nothing to do with the processing order. It'll always be async, but this is how we return the input stream is the same as the output. So it defaults to true. Timeouts. It defaults to 5,000 milliseconds, so you can give it either an integer or the atom infinity. And then on timeout is what happens when the task times out. So it defaults to the atom exit, which does exactly what we just saw, which is exit, or you can do kill task, which will only kill that certain task and not all the tasks in the caller. All right, so we're going to change it up a little bit with a chromatic scale. We're going to do a task async stream, do all of this, and set the max concurrency to 3, and then see what that sounds like. Fun. So as you heard, there's always 3 notes playing at once since we set that max concurrency. We're not really like looking at the terminal here. We don't care about the output, but the output is the same as the input order. And the exit, since we didn't have any exits, it would crash the stack if we had any issues. Timeouts. We talked about them a little bit just a moment ago, how it is either an integer as milliseconds, defaults to 5,000 milliseconds, or it is the atom infinity. So a way that we can force a timeout is just awaiting a task with 0 milliseconds. So if we run this, we get an exit of task await and then an exit as timeout. So that's what you'll see, versus what we saw before, which was like a runtime error when we were forcing a raise. All right, gen servers. Generic server, which is what a gen server is. It handles all sorts of processes. It monitors them for you, does a little bit more than task can do. All right, so this is the very, very simple gen server that we're going to be working with at first. You use the gen server, and then the only callback that's required is the init. So when you initialize it with the state that you want it to have. So you return a tuple of OK and then the state. There's other callbacks involved. We'll go into the 2 most popular ones in just a moment. And then how you start it. You can either start or start link. Both of those will register the name of the gen server, and then when the gen server stops or terminates, then it'll automatically deregister the name. So we're going to start ours with just start. We don't care about start link right now, with the name of the module and then the initial state, which is the notes. And it returns an OK in the PID of the gen server. So our most popular callback is a handle call. It's synchronous, so it's always two ways. We're sending a message out, or the server receives a message, and when we receive the response, we then update the state. So this is an example. We're doing a handle call. We're setting the request as play1 from, we're not using from right now, and then the initial, or the state of the handle call. And in this case, we're just spawning, again, like we did before, that play with the MFA, and then we're returning the reply tuple with the note that we just played, and then the new state. And how we call this is genserver.call with the PID of the gen server, and then the atom of the request name. And that is going to give us back the note that we're note args that we played, because that's what we say in the reply. Often we don't call genserver.call directly. We have some sort of wrapper around it, so it doesn't look like this. All right, so what does this look like, and how does this work? Cool, so as you could see, we just had to call play1 multiple times, and it just iterated through those notes because we're automatically updating state, right? We're getting a message, and then we're updating state after. Nope, go that way. Next one, handle cast, another callback. This is asynchronous. It's only a one-way message, so we're never waiting for a response to change the state. We're just moving on. So in this case, we do play cast, which is the request name, and then the state, which we're just putting to an empty list at this point. And then we're doing the same thing with the spawn, and then we reply a no reply, and then I'm updating state again. How you call this is genserver.cast with the genserver PID, and then a tuple of the request name, and then, in this case, the note that we're going to play, and that returns an OK. We are doing something ridiculous here for this presentation. This is not how you would call it. This is how we're calling it here. We're going to iterate through. We're going to map through those notes, and we're going to cast every time and see what that sounds like. Cool. So exactly the same as the async, right? Task async or await many. We're sending all those messages out. We don't care about the state to come back, so we're just sending them out and not really caring what happens. So how can this be a problem? There is something called a process mailbox for each process. It has a message queue. It only receives messages, it doesn't push anything out, and sometimes it can get overloaded. So the way that you can inspect it is do a process info with the atom message queue len, and then you'll get a tuple back, and then the second part of that tuple is going to be the number of messages in that process mailbox. All right. So let's do some more convoluted code here to make our example work. So we're doing the same handle cast. We're going to process sleep of 250 milliseconds right after our spawn. And then we're going to do the enum map, same code that we did before, and then we're immediately going to do a process info on the PID with that message queue len. And we see that we get 13 messages there. So we've already done one, and there's 14 notes total. So that seems stressful, right? Like, how do you know how many messages are there? How do you know, like, how do we handle this, right? What if you overload things? Back pressure. So the mailbox can overflow. That's fine. We just slow down the flow of messages. So again, remember, handle call is synchronous. You're always waiting for a reply. And handle cast is asynchronous. You're just throwing it out there, not waiting for the state to come back. And then if things get like really bad, you can just discard messages. So Logger does a really good, Logger has a really good example of this. You can read that code. There's also some good examples in the OTP book. So you can start with you can set thresholds for different things or for different message queue lengths. lengths that you want to do. So you can start synchronous with handle call, and then if you get over a certain threshold, then you can start doing async with the handle cast. And if it gets real bad, you discard, and then you can kind of go back and forth. Supervisors. So it supervises your processes, obviously. So there's a start link, 2 and 3. These create child processes. We'll talk about that in a minute. It notifies the parent when the child terminates. It can be started directly or in a module with callbacks. In this case, we're starting it directly in our example. Children, let's see if I memorized this correctly. It could be a list of child specs, which is a map, which has required keys of ID and start. There is a module that, as long as the module, you can give it a module as long as it has a child spec function on it, or you can give it a tuple with a module and an arg, I think, and then that will call child spec with that arg. I think that's right. Now, options to include, you have to include a strategy. The one you'll see most popular is 1 for 1. That's the one we're using here. 1 for all or rest for 1. 1 for 1 means if you start a bunch of children under a process and one of the children fail or terminates, only that child that terminates will restart itself. It won't affect the other children. 1 for all is if one child terminates, all the children will then terminate and then restart together. Rest for 1. The best way to explain this is just an example. You have process 1, process 2, and process 3. They're all children. They're started in order under the supervisor. So if process 2 terminates, the next process after it, and all the processes after it that started, will also terminate. So in our example, process 2 and process 3 will terminate, and then process 2 and 3 will restart. Whew. Glad I remembered that. Children. So this is our example, right? We're starting this without a callback, or without encode. So our children is just going to be this one child. We're using a simple gen server, and we're starting it with a tuple, the MFA, and then we start the link with the children that we defined in the strategy 1 for 1. In this case, it doesn't matter what strategy we have, remember, because it's all like about the other children. We only have one child. So that returns an OK PID of the supervisor. So then once that's started, we can call the gen server directly, right? We haven't started the gen server directly, but it's now supervised, so we can call it. So we can do the same thing like we did before, genserver.call with the name of our gen server and then the request that we're making play 1. Cool. So what I didn't say here, let me start link when it's starting up the children. In this gen server, it's actually playing a note when the gen server starts, and then also when we actually call the play 1. So you see supervisor start link, the OK PID, that's when it calls the gen server, and it's that's when it starts up the gen server process. And then when we call the gen server, it also plays a note. So cool. Let's throw another wrench. So in our handle call now, we're just going to raise. Oh no, something went wrong. And we're just going to reply with a note and note. We don't really care about state at this point. So what happens? So according to our strategy and according to what should happen in a supervisor, our start link has that PID, our gen server is the child PID, and then as long as something happens in the child when it terminates, it will restart itself, but the supervisor will stay up. So we can see that here. We start the link with a PID of 186.0. We call our function that has the problem. We get a runtime error. But then right afterwards, we can count the children. There's still one alive. We have which children. We see that the PID of the child has changed because it was originally 0.185. Now it's 0.192. And then if we call processed it alive on that PID of the supervisor, it's still alive. So it does what it says it should do, which is great. That's it. Thank you. My examples are here.